Hello everyone, my name is Dario Splendido and I am a lecturer in Creative Technologies at Bournemouth University and an Epic Games instructor partner. In this tutorial, I'll show you how to create fully modular buildings using PCG in Unreal Engine 5. This will allow you to create a very flexible structure that you will be able to use to customize your level. I will also show you how to use a separate collider to customize further your building with specific assets, like in this case with beams. Before we start, it's quite important that you activate the PCG plugins, because without those ones we won't be able to create PCG Graphs. The assets that I have used for this tutorial are from the modular building set, but you could use really any type of asset like megascans, and potentially you might want them for the tiling to be squared, because that will make your design a lot easier in terms of ratios, as you will see later on. Today we are exploring procedural generation inside Unreal Engine 5, focusing on buildings and structured environments. Procedural workflows are becoming a must-have skill across games, virtual production, and even architectural visualization. They let us build complex scenes quickly and maintain consistency while still offering variation. By the end of this session, you'll understand the core logic of PCG Graphs, how to set up basic rules, and how to use them to generate buildings or other modular structures. This is a great foundation for more advanced procedural pipelines later. Think of procedural generation as designing a system, not a single object. You build rules and Unreal builds the world. Procedural generation means the computer creates content following a set of rules. This is something you have all seen in games, roguelikes with randomized levels, forests that never repeat, and open worlds like Horizon, Skyrim, or No Man's Sky that rely heavily on procedural tools. Instead of modeling every building or placing every tree by hand, we design patterns and rules, and the system fills the world with variation. It doesn't remove the artist, it just shifts the role from manual placement to high-level design. This saves time, encourages experimentation, and lets us try dozens of ideas quickly. For level designers and environment artists, procedural tools bring three major benefits. Speed. You can block out entire areas in minutes instead of hours. If you want to adjust a street or footprint, you change the rule and everything updates automatically. Consistency. Because the graph drives the placement of meshes, everything follows the same style and spacing rules. No object floating, no accidental overlaps, no forgotten walls. Adaptability. Procedural systems allow for reactive environments. You can regenerate a village layout, produce damaged versions of buildings, or change clutter based on gameplay events. It is a node-based system designed specifically for procedural content. It works similarly to blueprints. You use nodes to control logic, flow, and data. The difference is that PCG Graph focuses entirely on generating things in the world: meshes, actors, splines, even data. A PCG component can be attached to any actor in the scene. Once active, it runs its generation rules, whenever the level loads or whenever you tell it to. What makes PCG powerful is that you can drive it almost on any kind of input. Mesh surfaces, landscapes, spline shapes, volume bound, tags, or even other PCG-generated data. This makes it ideal for buildings, vegetation, props, and anything that needs to follow patterns. To work effectively with PCG, you need to understand its core nodes. Input node is your starting point. It tells PCG what area of data or data it should use. For buildings, this might be a spline, footprint, or a simple box mesh. Scatter node is probably the most important node. It creates points, either randomly, evenly, in a grid, or based on density masks. These points become potential spawn location. Filter node. Because scatter gives you a lot of points, you usually filter them. You can restrict points by distance, slope, tags, probability, or any custom rule. Spawn node is the node that places the actual object. Walls, windows, props, roof pieces, anything. You can also add rules for rotation, scale, or random offsets. PCG Graph are modular. You can chain several scatter, filter, spawn processes to create more complex structure. A PCG graph is just a flow of inputs, points, rules, results. Let's break down a simple procedural building generator. Start with a spline that outlines the footprints of your building. This lets you draw any shape, square, L shape, curved, etc. Use a scatter or grid node along that spline to generate points where all wall modules will go. You can adjust spacing to match your modular asset size. Add a spawn static mesh node to place walls, pillars, corners, or window frames along those points. Add variation, random rotation, random mesh selection, adjustable height per floor. If you want multi-floor building, you can loop this logic. Duplicate the graph for floor 2, offset the YZ axis, and balconies or roof models. With this setup, you can draw a shape in seconds and get a fully assembled procedural building instantly. To push procedural building closer to production quality, we add layers of realism. Attributes and tags. You can assign rules per mesh, for example, windows only appear on certain edges, or specific floor. Levels use different materials. Blueprint integration, what door to auto-open, what random prop inside. Combine PCG with blueprints to give buildings interactive behavior. Seeding. Seed allows to generate the same building layout constantly. Change the seed and the building gets a brand new layout. Height rules. Add rules to higher floors, use different materials or reduce clutter, for example. Collision and nav mesh checks. Ensure your procedural building are game ready. This is where PCG becomes incredibly powerful. You mix artistic direction with procedural logic. PCG is not limited to buildings. Far from it. You can generate forests and vegetation systems, debris fields, clutter in interiors, crowd placement, road networks from splines, ruined environments, sci-fi corridors, even entire villages. PCG also works with data layers, meaning you can stream content in and out dynamically, depending on gameplay or camera position. In virtual production, PCG is used to quickly assemble background sets or to generate variation across shots. Once you understand PCG graphs, you can apply the same logic to almost any environment task. To wrap up, here are the main ideas. Procedural generation is about building systems, not single objects. Unreal's PCG framework gives you powerful tools for automating repetitive tasks. Building generation becomes much faster when you use rules and modular assets. You keep artistic control by designing filters, tags, and constraints. Start small, a simple footprint graph, then expand into a full system. PCG doesn't reduce creativity, it frees you from the repetitive work. You can focus on design, storytelling, and work building. The first thing we want to do is creating a blueprint class of the actor type. I always prefer to create a folder and save my blueprints in a folder for just having them quite ordered. But in this case, we won't have many. So the only thing we want to do is add a scene to your blueprint once you open it, and crop it there. So you want for your scene to be your main class. And then you want to add a box collision. And we'll just set it to 500, 500, and 500 in terms of scale. What we want to add as well, it is a PCG component, and that's everything we need to do here. We want to go back to our content browser, right-click in our folder, and find PCG. We want to create a new PCG graph and create a new one. We'll name it PCG Graph _ building. And we're gonna open it. But before we do that, go to your BP _ building blueprint, select PCG, and under the section graph, you need to select your PCG Graph _ building. The first thing that we want to do is right-clicking and get actor data. We do want a volume sampler because we want to have our blueprint showing us some volume before we actually put our buildings there. But we will actually add a volume size of 300, 300, and 300 for this tutorial. By clicking D, you will debug. As you can see, there is that blue dot that shows up on our node when we click D, and that will show us the volume. We want to add a bounds modifier and put it on set, okay? And then we want to set boundaries at -100, -100, -100 on the top, and 100, 100, 100 on the other tabs, as I did there. And this will showcase different meshes in our volume. Always by debugging, you'll be able to see if we are doing correctly. What we want to add now are transformation points, because we do not need for the volume to have all those meshes there. We want them only on the sides, okay? So on the offset min and max for the top one, as you can see, we wanted to put -150, -150 on the bottom one, and 150 and 115 on the top one. We want to create a difference node because, as I said before, we don't need all those meshes in our modular building. So we will remove everything that is in the center. So you create a difference node, you duplicate it, and you will connect the nodes as I did there. We also want to duplicate the transform points that we have there and connect the bound modifier to those two, because the two different nodes that we have there are just removing two of the sides, and I will show you in a moment when we do our next debug. So as you can see, there is a 150 on the on one of the wrong axes, so I had to remove that in order to fix that. So make sure that the 150 and 150 on the top one are just on the x-axis. Okay. So if we debug, we can see that we only have two sides, and they are on the correct position, but we want to have two more sides. So that's why I created the two more transfer points. And what we need to do now is put the correct offset, min and max offset, on the correct axis. And remember, for the third one will be 150 and 150, and for the bottom one will be minus 150 and minus 150. What we want to do is duplicate as well those different nodes and connect these new transform points to those as we did previously. Once we connect the last transform point to the last different node, we do debug and we have a look at our volume to see that all the meshes are just on the border of our volume, and that's what we need, right? So we don't want anything in the center. Also note that the rotation, min and max, need to be fixed. So have a look at how it has been done in the rotation area for the transformation points. Let's make sure that your transform points look like the one that I'm showing you now. So have a look at the correct axis and correct values for your offsets. What we need to create now is a union node, and we want to input all the different nodes into a union node. From the union node, you do create a transform point. And what we want is a static mesh spawner. On your static mesh spawner, under selector, you create a new index, and under descriptor, you need to go and find your static mesh and just apply it. So that will basically apply the meshes to our volume, but as you can see, there is a problem there. These meshes are overlapping, and quite significantly. So depends on the meshes you're using. That's why I was talking about potentially using like square tiling. That would make it a lot easier. If you're using something, the same assets that I use, please have a look at the offset min and max, and remember as well about the rotation of the assets if you have any problem, okay? So you need to go to the previous transform points. and that will fix it. Okay, it might require a little bit of either calculation, so you could come in and have that calculated already, or you can just have a look at mine if you're using the same assets that I'm using. Okay, now we need to create a ceiling for our building, and we're going to use a very similar technique. So from the bound modifier, you just need to create another bound modifier and put it to set. We do need to create bounds minimum and maximum, and will be -50 on all fields on the top and 50 on the bounds max. From this bound modifier, we need to create 2 transform points. And this time we're going to set the offset min and max. I will set up point 300 just as a starter and see where we get. So as you can see, we have more or less our meshes where they need to be, but we can always change them a little bit later to have them more aligned with where the ceiling should be. Create a difference node and just connect it this way. And we want another transform point. You can already imagine that after that, we're going to need another mesh, right? But in this case, I will show you how to change the material for that mesh, because that's something that might be useful. And also, I wanted to change the material because I used a plane from the same asset pack, and I wanted to use something else. So as usual, under the mesh selector, you create an index and you select your static mesh. You decide which static mesh it is. You could select it on your scene and even copy the name if you have it already set there. Copy and paste, and we have the mesh. So as you can see, that's quite a sandy type of material, and I don't want that. I want something that looks more like concrete, actually like the other mesh I have over there on the ground. So in order to do that, you need basically to override the material in your PCG graph. So you go on your PCG graph and you create an override material array, and under index you just decide which material you want to have and you just change the material. And here you go. I'm now going to fix a little bit the scale and the position for the rooftop, for the ceiling, to make sure that it aligns with what I have in mind and is a little bit precise. And we're done. What we're doing next is actually creating some beams and pillars that can go in our scene. So we just need to create another blueprint actor, and we'll call it BP_door. We just need to add a box collision this time, and we need to add a tag on it. So type tag there, and yeah, call the tag door, because we're going to call it on our PCG graph. So we go to our PCG graph and we need to get actor data. and we need to set it on all world actors. It must overlap self, so tick that box, and actor selection must be by tag, and just call the door. So you put door, you drag your blueprint door into the scene, and what we want to do now is test if this blueprint works, basically. So from your get actor data, you need to place a new node, and that node is going to be a difference node, okay? Because we want to test whether that node can basically delete our mesh. And yeah, as you can see, I have put the out into the difference and the transform point into the source, okay? And then you want that to go into your mesh. So it looks like it works. As you can see, it is deleting meshes, but we have not applied a mesh yet. So that's what we're going to do. You can create even more of these blueprints. So what we need to do now is just creating, adding our mesh. So from the transform point, we create an intersection node, and we connect the get actor to the source one into the intersection. And we just basically want another static mesh that will go and replace the meshes we already have on our modular building. As we did before, we just need to create under mesh selector, you need to create an array mesh entry, and you just need, under descriptor, choose your mesh. And I chose pillars in this case, but it could be anything. It could be doors, it could be anything that you, different windows, anything that you like to put in your scene. And yes, that is basically it. Yeah, you can test it. You can, of course, scale it and change it as well. All right, let's wrap things up by looking back at what we built today and why this workflow is so powerful. We started by introducing the idea of procedural generation in Unreal Engine, and specifically how the PCG Graph system let us create structured content using rules instead of manual placement. Rather than placing every wall, corner, or window one by one, we let the system handle the repetitive work for us. In this tutorial, we used that workflow to create a fully modular building from just a handful of meshes. The foundation was simple. We gave the PCG Graph a shape to work from, and then defined how the system should fill that shape. By scattering points around a footprint and spawning modular pieces onto those points, we built a controllable, repeatable construction pipeline. Even with a basic set of rules, the PCG Graph was able to assemble walls, align corners, and maintain consistent spacing for us. And the great thing is, changing the footprint of the parameter can instantly generate a new building. One of the most useful tricks we can explore is the box collision method. By assigning a box volume as the input for the PCG Graph, we gave the system a clear boundary, only built inside this region. This means we can resize the box, move it anywhere in the level, and the PCG Graph will automatically regenerate the building inside that new space. It's a new incredibly and flexible way to prototype structures, perfect for blocking out environments quickly or iterating on building shapes without having to remodel anything. So in just a few steps, we combined a simple modular kit, a scatter, filter, spawn workflow, and a collision box that drives generation to create a procedural building system that is dynamic, clean, and completely reusable. The power of this approach is that everything exists as a rule, not a fixed design. You can change the seed to generate variations, swap the meshes for different architectural styles, or layer additional graphs to add props, windows, roofs, or even interior details. If you take anything away from this video, let it be this. Procedural tools don't replace creativity, they speed up experimentation. They help you iterate faster, try new ideas without penalty, and build environments that feel alive through variation and control. Thanks for watching, and I'll see you in the next session.